In this video, we're going to be looking at our model assumptions that we're making when we're doing linear regression and ways to check to see if they're met. So like I say, the unfortunate thing about math is that no one is going to stop you if you use the incorrect formula. As long as you're putting numbers in, you can literally use any formula you want. It doesn't mean that the outcome is going to be useful. When we are doing inference on our regression line, when we are trying to do prediction, trying to decide how good of a prediction we have, we are making assumptions. In particular, we've been making that assumption about the normal error terms. And if these assumptions aren't met, we're going to fall under the garbage in, garbage out criteria. No ninjas are going to come from the back of the room and stop you from using linear regression, but if your model assumptions aren't met, it really doesn't matter what your output says because it's inappropriate to use. Oftentimes in classroom settings, we just say, here's data, this is the correct method, go and analyze it. Now, we're not going to spend a lot of time talking about model assumptions in this class, but I want you to be aware of them, that it's very important that when you collect data in real life, no one is going to tell you what's the correct method to do. No one is going to tell you whether or not your model assumptions are met. No one can just look at this data set of 100 things and say, oh yeah, totally a normal distribution. You need to decide these things for yourself, that you're going to have to go through these steps of testing whether or not these are reasonable. So we're going to look at those assumptions that we're making for linear regression so that in the future, when you go and collect data yourself that you want to do linear regression on, you're aware of the things that you should be checking for. So just like we had assumptions, match pairs was something we talked about, having the related pairs, it was very important. We're going to have that same assumptions coming around here. And again, it's going to be centered about that idea of normality. Match pairs, we had to have that the differences followed a normal distribution. And we had that warning that in class, I'm just going to say, assume these differences are normal. That's generally speaking not reasonable. If you have a small data set in real life, you should be testing it. Either have enough data that the central limit theorem is kicking in when you're looking at averages, or you need to be really careful. So the model assumptions we're going to be making, and again, these are mostly around the fact that we had that our error terms were normal with mean 0 and standard deviation sigma sub epsilon. So number 1, we have the expected value or the mean of our errors is 0. Now, luckily for us, this is going to be a freebie, but hold on to our horses. We're going to have that the variance of the error terms is constant across all values of y. So we'll visually see what that means, but that has to do with all of the errors have normal distribution with that same sigma value. Our data set is linear, i.e. you're actually fitting a line to something that follows a linear shape. You're not putting it to something that is clearly, quadratic. This would be a bad data set to fit a line to. You could put the points through the formula and it will give you something. That doesn't mean it's meaningful. 2, our probability distribution of the error terms is normal. And 5, that our errors are independent between our observations. And this one, unfortunately, or fortunately, no formal test that we're going to be looking at, but we're going to be using common sense approach to this. So let's look at our model assumptions individually. The first one says that our error terms have expected value or a mean of 0. And we get this for free because y hat is specifically made so that the errors would sum to 0. For every point I have above the line, I have the same amount below the line. And this makes sense that if my errors averaged out to 1, I should just shift my line down 1. If this was giving me an average of too much errors on the bottom, so we had all these errors here and very few up here, well, maybe what I should just do is shift my line to make it more centered. It wouldn't make any sense to have errors averaging out to anything but 0. So this one, we say, my favorite way of saying it, this is true by construction. the way we use our math to create the beta 1 hat and beta 0 hat is automatically going to give us the error sum to 0. Model assumptions 2 and 3. This says that the variance of the error terms is constant across all values of y, and 2, that our data set is linear. So let's remember what it means to have constant variance. If I were to draw a picture here, we mean at all of the possible x's that I have, that the spread of my y's is about the same throughout. So I have the same amount above and below, and that spread of points is approximately the same. So I would get 2 lines that are parallel to my actual line, and everything is going to fit in that constant spread. This would be good constant variance. And 3, the data set is linear. That's what we said. Our points, it makes sense that the underlying relationship is actually a line. We're not trying to fit a line to something that's obviously a quadratic or a sine wave or a cubic relationship or something like that. Now, the way we do this is by making a graph called a residual plot. So what our residual plot is going to do is it's going to take the predicted values and put them on our x-axis, and we are going to plot our error terms here on our y-axis. You can imagine that we would have some sort of imaginary line here around 0, because our errors sum to 0 or average out to 0, so we should have equal amount above below the line like that. So what we're trying to discern when we're looking at this residual plot, we're looking for 2 things. One, that I have no sections of my plot that appear obviously taller or wider than other ones. So I'm looking for things where my points are about equally spread up in the up-down direction. So if they're spread equally in the, think about the up-down direction in my plot, this is going to be our indication of constant variance. And we can see this makes sense because this says as I go across my y hat, which really every y hat has a unique x, so you could really think of it as I'm increasing my x, I'm seeing about the same amount of error. That if I had a plot that looked something like this, that would mean that I have a lot of error in this one particular section of y, and then my points are very close and I get later on to a later y hat. Maybe think of it as a y hat star. What would this look like on our regression line? Well, it would look something like this at my y hat versus my y hat star. So at this value, we're going to see a lot of errors, but at this value, we're going to see very little. So that's kind of what that plot would look like. Very little spread around the y star value, but increasing spread as we get to here. So we can notice that is not a constant variance. Our other thing that we're going to get is we're looking to see if our data is linear. The way this appears in the plot is make sure that we don't have a discernible pattern inside of our plot. So our points appear spread out at random, that there's no systematic favoring. So here, this is something that would not be linear. Again, thinking this is our y hat versus our errors. If I had something that looked like this, I have a clear pattern. How would that look like in my actual regression line? So that says as my y's, and here let's put an imaginary x equals 0 line, that as my y's get bigger, or as my x's get bigger, I'm going to see this bending. So this would look something like this. So you can see what's happening here is really I have something that looks more maybe not logarithmic because it's leveling off, but it's clearly not a linear relationship. There's that curvature that's going. When you have things that are really curved and not in a straight line, that's when they're going to start appearing as kind of these quadratic functions inside of our residual plot. So this would be bad. Whereas this one, if we again pretend we're just looking at the green stuff and not the pink stuff, I have no discernible pattern. That would be an indication that we actually had a linear relationship. We don't want any systematic patterns in our error terms. Otherwise, that would suggest a specific deviation from our line. So if I want to do this in R, we're not going to ever do this by hand because this is just a scatter plot. We're plotting the y-hats versus their error terms. I'm just going to use the scatter plot function, my plot xy. And we are going to use it in order to plot my fitted values against my residuals. Now this is going to be just learn a little extra skill here. So what we're going to do is we were using that LM function in order to get our coefficients for our regression line. If we save it to an object, so instead of just going LMY tilde X, and I instead save it to something, I can tease out more information. Just using the function will spit out my coefficients, but if I save it to an object, that object is actually going to store a bunch of different information. So once I store it in an object, I can use the resid in the fitted.values function to pull the residuals and the predicted values out of that object. So we want to think here as an example. And remember the vectors we were using were life and fertility. So that was our y. Our LM of our y tilde x. So the life.lm, I am going to save that function to this object. And we'll note that R won't print anything out because I'm just storing it somewhere. I'm not saying print this, I'm saying make this object. So the way that I like to conventionally do these, and this is a me thing, is I like to give some sort of descriptor of data dot descriptor of object. So this is really a thing about life expectancies .lm. I'm saving the linear model in this. Truthfully, you can call it anything. It's bad practice to call it anything. You should put it something that's going to be meaningful to you, but also to someone else who might be using your code, and not just meaningful to you now because you just saw this weird inside joke on some Twitter feed or YouTube video or something. It's 6 months from now, 5 years from now, you is going to be able to look at this and say, oh, I stored a linear model inside of this object. That's what I was doing. So I create my object, life.lm, and then I'm going to apply those two functions, the resid and the fitted.values functions. Now, it's important that I am not just applying the function, I'm actually storing the output into an object. I don't want R to list the residuals, and that's what it's going to do if I just write resid life.lm. It will just print them out. I don't want them printed out. I want it to save them so that I can use the scatter plot function. So I'm going to save this into this thing called life.resid. So again, descriptor of the data set I'm using, the life data set about life expectancies. What am I putting in this object? I'm putting the residuals in this object. And then we can do the exact same thing for the fitted values. So I apply the fitted.values function to the life.lm object. And then I'm going to say I want to save this to an object. So I'm going to call it life.fitted. Descriptor of my data set, life.descriptor of what's in the object, it's the fitted values. Now using that, I can use my plot function. So plot, we said it was plot x comma y from when we were doing our scatter plots. So plot, my y hats go on the x-axis, so that's why I'm putting my life.fitted there. And then comma my y, I want my error terms on my y-axis, so that's my life.resid. Residual is the same thing as error. And then I go and because those are kind of dumb names that aren't really helpful to anyone else when I'm actually making a scatter plot, I'm going to put better labels on my x and y axis, otherwise they default to the object names. So I am going to call my x-axis my y hat to remind myself that we are fitting our y hats, and I'm going to label my y label as residual, and then we can use that main option to give it a title. I'm just going to call it residual plot. So what does this look like when I go and I make my plot in R? Let's make this a little bit smaller so that we can see. Move me away out of the picture for a second. So what we're going to see is I have this scatter plot, and I'm going to notice that I have about an equal up and down spread throughout the plot. There's no areas that seem tighter or wider than others, and I also don't see any clear pattern. All of these objects are being spread about at random. And about same plus minus throughout, randomly dispersed with no clear pattern. So like up, down, about the same width throughout means we have constant variance, and the no clear pattern means it seems reasonable we have the linear relationship. Now, sometimes it seems very obvious that we have a linear relationship, and it may feel like you don't need to do this. I have one great example that I came across while doing one of my classes that it looked like your points were super, super tightly fitting to the line. Like anyone would have looked at this and said, this is like the clearest linear relationship I've ever seen in my life. And then we did the residual plot, and it was whoosh, quadratic equation. And what was it? It was a severely logarithmic relationship. It's just the scale was so tiny that we couldn't detect it when we were looking at it zoomed out as a line. You had to really, really zoom in, but it was a super obvious logarithmic relationship, but you had to get the scale like super blown up before you could see it. Don't always trust your eyes when you're looking at scatter plots. The residual plots are incredibly important. Not a step that you can skip on or decide to skip. Now, our next thing that we're going to look at is our plots for trying to decide whether or not we have normal error terms. So for these, we are going to look at what's called a normal quantile plot. So we've seen these normal quantile plots before. What we're doing is we're putting in our data, and we're trying to see in the plot, do the points fall closely along the line? Because it will take the actual values that you see and plot them against their theoretical z-scores as if they were normally distributed. So if our data set was perfectly normally distributed, our actual values would match perfectly with the theoretical z-scores, and they would fall across the line. Now, to make this a little bit easier to read, what we first are going to do is we're going to take our error terms and we're going to convert them to z-scores. So we're not just going to find the residuals, we're going to find these standardized residuals to make it look a little bit nicer when we're plotting them against the theoretical z values. So we will go and we are going to make an object of our standardized residuals. So think z-scores, think of this as our residuals converted to z-scores. So I think my error minus what's the average of my errors, we said the errors average out to 0, divided by what's a standard deviation of my errors. So that's that constant variance that we have in our plot. And then just the same thing we've used to create normal quantile plots before, QQ norm of the standardized residual, that will make the plot. And then QQ line is going to add the straight line to make it easier to read. So I make my standardized residuals of my life.lm object, and I'm going to save them into something because I don't want R to print them out. I want to use those standardized residuals. So life.rstd, that's how I like to abbreviate it. QQ_norm on that standardized residual object. QQ_line on that standardized residual object. And we will get this normal quantile plot. And we'll see that our points fall fairly nicely to the line. Our points are close to line. So this is going to imply to us that it seems reasonable that our errors are normal. Now, I'm being very careful that I'm saying here that my errors are normal. Don't say the data is normal. Don't say the y's are normal. It's specifically the error terms that we are looking at. We are not at all claiming that any of our data is normal. We're claiming that the error terms are normal, and that's a very important distinction to make. You never want to interpret a normal quantile plot by saying the points are close to the line. That means my data is linear, or even worse, it is linear, normal. You don't want to say the data is normal. You don't want to say it is normal. What is it? The error terms explicitly are normal when we're testing our regression assumptions. Don't use vague term it. Be very explicit that you recognize it's the error terms that we are testing. Then our last assumption, that our error terms are independent between our observations. We're not looking at tests for this. There are some tests for independence well beyond the scope of what we're doing here. Most people, what you're going to be doing is this about active ethics, thinking about how the data set was collected. Does there seem to be any reason why our error terms or our observations are going to be affecting one another? So if I know Lithuania was 3 above the expected value, does that tell me anything more about Rwanda in my data set? And it seems likely to us there's no logical sense why how far off Rwanda was from the data set that it would affect how far off Bangladesh was. They're different countries, and it's purely about fitting our model, so it should be independent. Ways you might get non-independence is if, say, you're doing a designed experiment and you're collecting data that's happening over time, and as you are doing your experiment, maybe your machine starts to decalibrate and your measurements get further and further off. So at the beginning, your observations are pretty tight to a line, but near the end, as you're getting worse measurements, they start skimping off and getting more and more and more varied as you go on. That could be a reason why your errors aren't independent, because there is a time factor to the way that you have collected them. That could be a reason why it's not working. So this is more about thinking logically, did I collect my data appropriately? This is a designed experiment. Did I do my best to try to avoid time effects where we could use one is going to predict what's going to happen in the next one? Those are our model assumptions. This is not going to be a very big part of the course. This will be something that you explore more in later statistics courses, but I want you to take away from this is that this is something you should be doing when you're collecting data and you want to do a linear regression. You should be thinking about these model assumptions before you start doing your inference and before you start doing hypothesis tests and deciding, is it a good fitting line? You want to ask, was it even reasonable that I'm doing regression in the first place? It's a very, very important step to take as a statistician.